Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
I'm very pleased to announce Mark Guzdial from Georgia Tech. Mark Guzdial has many different relationships with Microsoft. He is the PI for our robotics effort in CS curriculum that he does with Stuart Tansley, and he's not talking about that, unfortunately, today. He also has a great presence with our Academic Days cruise. He's at one of the most highly rated talks, and that's what we brought him back here for. He has a really innovative way to make computer science attractive, not just to us who are already at Microsoft, but to folks that have never even considered computer science. And if he's successful, then our industry will get a whole lot more diverse. So let's welcome Mark Guzdial.
Thank you very much, John. Thank you. So, as John said, this is a talk that I gave on the GDCSE, the Game Development for Computer Science Education, the Games Cruise. So here's the story. I want to talk about how important computing is for everyone, and particularly give the context of how Georgia Tech decided in fall 1999 that every single student that came onto the campus had to take a course in computer science, and why they made that decision. Making computing work for everyone is not something that computer scientists have been very good at. There's a lot of things that make it very difficult. Our models about how we teach computer science don't extend to everyone very well. So I'm going to talk about media computation, this approach that we developed, in particular for teaching the liberal arts, architecture, and management students on campus about computer science in a fairly rigorous way. One way of thinking about it, and we have this in both Python and Java for both CS1 and for a data structures class. And by the way, I would be happy not to take all these books back home with me, so please feel free to grab one. This is both the CS1 textbooks in both Python and Java. One way of thinking about this that was particularly relevant for GDCSE was that in some sense in this class we're talking about how we implement video and audio effects that are common to gaming. Echoes of sounds, reversing sounds, background subtraction, and chroma key. These are techniques that typically the game engine might provide for you or the API. We're teaching computing and finding that students are attracted and being retained in this approach, explaining how those lower level things work. And then this is an approach that connects well to other approaches. I'm going to talk a little bit about the Allison Media Computation and the work. So we'll touch briefly on, as John was talking about, I'm involved in the IPRE effort, Institute for Personal Robotics and Education, merging media computation with some of that. And then I will give you some assessment results, particularly because Jamie's in the room. But I was going to do it anyway. All right. So in fall 1999, Georgia Tech decided that all students at Georgia Tech must take a course in computer science. Why? Most of the reasons at that time were, well, they were broader than just computing's good for you, take your medicine. It wasn't that sort of thing. First of all, Georgia Tech had just decided, as Carnegie Mellon University did, almost the same time, I think CMU was actually slightly earlier, had decided that computer science was important enough that it gets a dean and it sits at the dean's table. So we became the College of Computing. And there was actually thinking on campus, well, if it's important enough that we have a college, it's important enough for everybody to know something about it. There was also the sense that scientists and engineers recognized that computational science and engineering was the future of the field, and that we bring computation into science and engineering to help us understand things in science and engineering. That computing serves as a tool for improving the understanding of professional scientists and engineers. Well, if that's the case, if it is a tool to aid in understanding, doesn't it make sense to provide the same sort of tool to students? In some sense, we can tell stories about telescopes and microscopes originally developed for the astronomers and biologists, but eventually we say, you know, it helps the students too. And so there was some thinking about bringing the computing to the science and engineering students. Surprisingly, the liberal arts college was actually in favor of making this requirement for absolutely everyone. Somewhat surprising was for me. You actually agreed with this requirement. For them, it was a way of differentiating their students from all other liberal arts students. That here we have a liberal arts college at Georgia Tech. Well, that's something kind of unusual to have a liberal arts focus in an institution known for science and engineering. Well, we can really take advantage of that by leveraging that place by requiring the liberal arts students to take computer science as well. So in the nearly 10 years, we have been trying to figure out how to make this work. And Ken Perlin, in his, one of the opening addresses for GDCSE, made the point that he's realized that the critical issue of end-user programming is why. Why would you want to program? And answering that question is really the critical thing to answer in order to be able to get computing science for everyone. Today, though, we can actually come up with even more reasons than the ones which existed in fall in 1999. This is a quote from Richard Dawkins, arguably one of the most famous biologists in the world. And when he was on Fresh Air with Terry Gross, where Terry Gross asked him, you close your book saying, I am thrilled to be alive at a time when humanity is pushing against the limits of understanding. How do you think that's happening in your field of evolutionary biology? You can read the whole paragraph, but the killer sentence is, since Watson and Crick in 1953, biology has become a sort of branch of computer science. Here's one of the most world-famous biologists saying, we're just computer science. And there's a good argument for why biologists and everyone who would study biology should know something about computer science. So I'm going to occasionally throw up some data up here. Don't worry, you don't have to know all of it, and there won't be a test later. For the first 4 years of our requirement of everyone taking computer science, we offered one and only one course. Originally it was in pseudocode, and then we moved to the Teach Scheme, How to Design Programs approach. This is, time is actually going, so this is 0-1 fall up to 0-2 fall. You don't have to look at all the numbers. The general thing, the pass rate here is fairly low. All right, we're looking in the 60 to 70% range of the students are passing the class. And sometimes the women are failing at almost twice the rate of the men. This wasn't a very good thing. And in general, what we're looking at is that this is Georgia Tech students. Georgia Tech students are really pretty good, and we're flunking them out at these numbers. What's going on here? Shouldn't we expect that a smart student should be able to get through an intro computing course? So what we came to decide is that what we need is contextualized computing education. Is it a problem for this if I walk around at all? Okay, great, thank you. So since spring 2003, we now teach 3 intro computer science courses. Our approach has been informed by the research that has gone into what's wrong with computer science education. Notably, books like Jane Margolis and Alan Fisher, Unlocking the Clubhouse, Women in Computing, where they point out that we ought to offer alternative paths to computer science. Not everybody comes with the same background, not everybody comes with the same interests. We should have multiple paths into computer science. They talk about, explicitly in there, that students come to computer science classes, if they come to computer science classes, and as we know today, that doesn't always happen, because they find that things like BlackBerries and tablet PCs, the fact that I can draw on the screen, and Wii's, and all of this cool technology in our lives, that's why you come into class. And then once you get to CS1, we tell you how to compute Fibonacci numbers and how to solve Tower of Hanoi. There's a clear disconnect, and the students say we don't see why it's relevant, that they see intro computer science as relevant. So each of the courses that we now teach have a particular context. All of the examples, the things we do in lecture, the homework assignments, are all connected to a context which is relevant to those majors. So we now teach 3 CS1s at Georgia Tech. There's one for our majors, our computer science majors, and the majors in the College of Science. This is the one which is now all robotics. That's the one that we're doing with the Institute for Personal Robotics and Education. We have one for the engineers, where the programming language is in MATLAB, and all of the problems are drawn from an engineering context. They figure out what is the launch velocity to get a rocket ship outside of Earth, into Earth orbit. They figure out things like the flow of fluids from one tank into another tank, given a certain configuration of pumps and pipes. These are real engineering contexts, and the students buy into that. And finally, there's the introduction to media computation, the intro to computing for the liberal arts, architecture, and management students. I'm not going to say too much about the MATLAB course. It's the latter one, which is the one that I was tasked with and that I've been trying to develop for the last few years. I will give you a little bit of the results from the engineers. As I showed you a moment ago, that in general, the CS1 for absolutely everybody on campus, we're looking at 60 to 7% success rates. We did a lot better when we gave the engineers an engineering context. So here's our first piece of data that maybe this context idea really has something, that the engineers are doing better now than the whole campus was thrown into one class. So I was tasked with teaching the liberal arts, architecture, and management students. And if you think about it, this belief in context, you realize this is actually a very challenging problem. In general, computing does not pervade the professions that are engaged in liberal arts, architecture, and management, not in the same way that they do in science and engineering. In particular, we don't know a whole lot of architects, for example, who program. It's hard for me to convince an architect that it's worthwhile for you to program. So I had to figure out a story that I could tell in order to make that make sense. And so the story we said was that for these students, Computing is less about calculation and more about communication. That what these students are going to do with a computer is communicate things, work with digital media, create PowerPoint, work with things like Windows Movie Maker and iMovie. That's the context in which we want to talk about computation. So we cover the same kinds of computer science. If you take an intro computer science class anywhere, you're going to iterate across all the elements of an array and compute the average or find the maximum or things like that. How about if we iterate over all the pixels of a picture and compute the grayscale or compute the negative? We always iterate across a particular range. Maybe we're going to change one string and change all the letters to something else. How about you iterate just over the pixels around the eyes to remove red eye without changing the red clothes that somebody's wearing? We talk about algorithms as a general recipe or process that crosses different kinds of data. So it turns out that the algorithm by which one sound fades out while another one fades in is exactly the same that used for blending two pictures and having some degree of transparency. It's the same algorithm, just applied to two different kinds of media. In the data structures class, we manipulate linked lists. We always manipulate linked lists in a data structures class. One of the things you commonly do in a linked list with data structures is you take a node and you make 5 or 6 copies of it. And you take another node and you say, skip a 2, put 1 in, skip 2, put 1 in. You take another node, skip 1, put it in, When these nodes contain numbers or strings, this is one of the most boring activities in the world. When the nodes contain MIDI, you are creating Western music. You specify a motif, you recapitulate the motif, you have a variation on the motif. A linked list ties very well to Western music, which is a strange thing to think. It's sort of like, why didn't we do this earlier? It's a lot more compelling for the students. And it allows us to get into ideas that are really important, really big ideas of our field that we don't normally get to in an intro course. This picture here is the words, this is a test, where each pixel gets mapped, each sample of the sound gets mapped to 1 pixel, and then we choose the color based on the value of the sample. This is a sound visualization. Now we have some idea of how Winamp does it. Then we write another piece of code that takes this picture and turns it back into the sound. Strangely enough, you can hear the words, this is a test. It comes through pretty clearly. And now you get this idea of information being separate from whatever media that it's encoded within. And that's a really powerful idea. You just sort of watch the kids explode when they see that. So media computation is showing up in undergraduate classes and high school classes, teacher workshops. As I said, we've originally started doing this for our course at Georgia Tech. We currently have 300 to 400 students a semester now. Unusually, it's about 51% female because of the majors who take this class. It's required in the liberal arts architecture and management programs. One of the cool things about this class is that it has been one of the things which has enabled us to create a new Bachelor of Science in Computational Media, a joint degree between the College of Computing, particularly the School of Interactive Computing, and the School of Literature, Culture, and Communications in our Ivan Allen College of the Liberal Arts. That sort of degree program wouldn't have existed if it wasn't the case that you could now get liberal arts students to succeed in an intro computing class. That program in particular is 27% female, which is dramatically different than most computer science undergraduate programs around the world today. Soon after we did the Python version, Barbara Erickson, my co-author, and my wife, did the Java version in order to help high school teachers learn computing through a media computation approach, and that's what the red book is here. Later we've done the data structures in Java, and now there are schools that are using this approach in their computer science AP classes, their advanced placement classes, and now we're integrating media computation with other approaches like Alice and the robotics approach. So just to give you a sense of what this code looks like, we're going to show a couple examples later on. So here's Santa Claus, okay? And here's a piece of code for removing all the red in that example. Define the function clear red on a picture. For pixel and get pixels of the picture, set the red of the pixel to 0. And that gives us the green-blue kind of Santa. Quite straightforward. One of the things that's nice about Python, for those interested in sort of pedagogical aspects of programming languages, the for loop in Python is actually a for each, which means that you're saying explicitly for each pixel in all of the pixels of the picture. We actually know from a lot of research dating back to the 70s that without knowing anything about programming, a natural way in which people specify loops is not by looping, but by specifying qualifications. You don't say, now go through this stack of files and find all the last names that start with G. You simply say, give me all the last names that start with G. You don't say, check each one and make sure the first letter is G. I mean, you specify as a qualification, as a specification of a set. And that looks more like a set operation. So we can start playing with iteration without getting through the notion of iterating through the loop over and over again. If you know something about RGB, and it's very weird to say this with Jim Blinn in the room, you know that to get a grayscale, you want the red equal to the green equal to the blue. It turns out that a reasonable way of getting the right value to set that is to simply average them. It's not great, but it works. And so here we're simply getting the redness, greenness, and blueness, computing an average, and setting the color of that pixel to where the red, green, and blue is all the same luminance value. And we get a reasonable grayscale Santa. How do we negate a picture? Well, each of these red, green, and blue values varies between 0 and 255. Turns out that if you simply subtract 255 from that, you get the reverse of that amount of color. So we're going to create the negative by making a new color, 255 minus the red in the red slot, 255 minus the green in the green slot, 255 minus the blue in the blue slot, and we end up with the Goth Santa dark elf look. One of the really neat things about this approach is that we can give quite open-ended assignments in the class. I want you to make me a collage, and I want you to have the same picture appear at least 4 times, the original version, and then do anything you want to the other 3 with the same picture. Scale it, crop it, make some other cool manipulation to it, and then place these all on a canvas and then mirror them horizontally or vertically. And thus we get these kinds of images. These are not from students. I'm cheating a little bit here. These are actually done by teachers in a teacher workshop that we ran last summer. The really cool thing is they started first thing in the morning, had never seen Python, and they did this during their lunch break. It was really pretty easy for them to get started in doing cool things. We do similar things for the other media that we introduce. I would like to see a movie. Oops, I should move this into an arrow. I want to see a movie where at least 3 things are in motion at once. I want to hear a sound collage where the same sound appears multiple times. We can similarly do things that I was telling you about with the linked list. A canon is a natural kind of a music structure that arises from manipulation of a linked list. Oops. I don't know why. There we go. All right. So I want to give some more specific examples for folks from computer science teachers who want to see exactly how this works. So I'm going to give you some examples from simple audio effects and some examples from image manipulations. When you were in physics class and you were told about how sounds combine, you had all this stuff about reflections and troughs and waves. It turns out that those of us in computer science have life much easier. If we want to combine 2 sounds, you simply do addition of the same elements in an array. If you're not familiar with how digital sound works, is that a sound like this, oops, back to an arrow. A sound like this is actually an array of sample values, which is the amount of pressure hitting the microphone at any moment. And these values vary between positive and negative 32,000, roughly, 32K. So this might be 10, 11, negative 100, and so on. And the way that you add sounds is to simply take this plus this goes into that one. And you simply do that across all the elements. And thus you're able to combine sounds in interesting ways. Which, here's a very simple piece of code that simply does that. Walk through all the values of the sound, grab the 2 samples, add them together into the bottom sound. Once we can combine sounds, we can do blending of sounds. We can do all kinds of things. We can do echoes. We can create choruses. We can create, by simply adding sine waves together, we can make instruments that don't exist in the natural world, and by doing something called additive synthesis. So there's a lot of really cool effects. One of the really fun things we do is reversing a sound, and I actually want to show you a piece of code here. Okay, so this is a sound that I recorded on the way in. Oops, play sound.
Welcome to Microsoft Research.
That was Kent. Normalized a little bit, and actually the code for normalization is in here. We simply walk through, get a maximum, find out how to compute the maximum value, multiply that multiplier by everything. And then we can play the reverse sound of that, which is we get by running the backwards code on that. Now, if you look at the backwards code here, all right, for all the computer scientists in the room, you look at this code and you say, oh, well, this is simply reversing an array. You have one pointer that begins at the end, the beginning of the array, another pointer that begins at the end of the array, swap values from the source to the target, decrement one, increment the other, and keep walking that way. This is a really simple thing that you do in just about every CS1. But when you reverse an array, like, who cares? But when you reverse a sound and you get to make Kent sound funny, it's a lot more interesting. It's a lot more motivating. And that's the kind of thing that we're after. How do we make this scene turn into a sunset view? We play with things in the class. We try incrementing the red. We found that another way of doing it, rather than incrementing red, is to decrease the green and blue. And so here's a simple piece of code that does this. We tend to do this live in class, try out different examples. Reducing the blue and the green by 30%, as you see that this code does. I don't have to tell you much about Python. You sort of look at it and you get the idea. You get a reasonable sunset view. Now we can take this and do this as a video. So here's a piece of code that's going to grab that small beach scene, and for 100 frames, run this piece of code, which decreases the blue and green by just 1%. And just 1% means that over 100 steps, we eventually remove all of the blue and green, which isn't actually what you want. I mean, up to here, it's sort of a cool sunset. At this point, the sun has gone supernova, and all life on Earth has been extinguished. But we can turn this into a movie. Oops. And about there, all life on Earth is extinguished. Okay? So it's a pretty simple step then to go from a simple image manipulation to something you do over 100 frames and produce a little tiny piece of video. We play with a little bit of background subtraction. For those not familiar with background subtraction, you have a picture of a background without a person. I have a picture with a person. Which pixels are the person? Well, if you have the background and you have the background with the person, all pixels which are the same in those two pictures must be part of the background, and the rest of it is part of the person. And so we can swap the background by saying if the pixel is the same in both pictures, go take a pixel out of someplace else. And thus what we can do is take my daughter standing against a wall and put my daughter standing in a jungle or a forest scene, whatever it is. Now, there's flaws in this. There's lots of flaws in this. One of the problems is that my daughter's shirt matched the color of the wall pretty closely. And so pieces of the jungle shine through. It's also the case that I was absolutely awful with the lighting. You can see where the light was. The light was over here, and part of her shadow seems like it's part of what's going on here. Now, we can tweak that. We can play with threshold values, because what you're doing is saying, how close are these two pixels to one another? And by increasing the threshold that you'll accept, changing that threshold value, you can make more and more and more of it match the background color. And actually, we can take that and turn that into a movie. All right, so we're changing the threshold value as an input. You run this over the 100 frames. And now we take two people standing against a wall, plus a picture of the wall, and slowly have them fade into the jungle. And then we can turn that into a movie. Now, but that's using the jungle as the background. What if we simply use the blank wall as the new background that we're bringing in? Then we get sort of a transporter effect as they slowly disappear. Andy.
I just forgot.
It was when I was doing this movie.
Are you creating the movies live so they can see, as the Python code is working, they see the graphics at the same time? Or do they have to run it, save it to a file, and then open it up?
The latter. Currently what we're doing is we take some video, or in this case, these are just standard pictures. We're generating 100 frames. We then take the 100 frames, put it into a movie, or we've written little players that will simply play the JPEGs as if a movie. And we can pull in from disk fast enough that we can get at least 15 frames per second. And that's about all that we really need to do these sorts of effects. Now that we know that a much better way of doing that sort of identification of where's the person and where's the background is using something like Chroma Key. Chroma Key is where the background is a known color, typically blue and green. Actually, in the class, we'll take pictures of somebody in front of a red background and try to wipe out the red, and we find that it doesn't work. You're giggling, so you're familiar with this. I mean, there's a whole lot of red in our faces, and so just about any time you try to use red as the Chroma Key background, you end up splotching all over their face, which is where you get the idea of how they have some really great monster effects, probably got developed in that way. So here's an example. It's really, I mean, this is not great Chroma Key. And actually, the algorithm we teach is not the pure Chroma Key. We don't actually mask and then apply a mask. All we do is look for where it's blue, pull in the pixel from the new background. And so here we go. This was actually my son's blue sheet that I attached to the entertainment center and took a picture of myself with this. And then I put myself on the moon. obviously, that I've done this poorly. You can see edges in the moon, which didn't show up when they used the same effect for faking the Apollo 11 pictures, for example. Yes?
Was that added by some software?
I did have a mustache until last April, yeah. The former students in the back row are saying, yeah, he used to have a mustache. He really did. All right, so this example I can show you in Java. We've actually done this all in Java as well. So all we're doing here is we're walking through, for every x value from 0 to the width, for every y value from 0 to the height, we get the distance between the current pixel's color and some fixed color. If the distance is less than some threshold distance, get the pixel from the new background and set the color of this pixel to the color from the new pixel from the background. And thus we can swap out the moon. And then here's just a piece of code where we're grabbing all of the frames from a particular directory. This is a directory formed by my children crawling on the floor in front of the same blue sheet on the same entertainment center. However, this is actually a negative example, which is actually fun. One of the cool things about this approach is that even the negative examples are kind of fun to look at. I was doing this at night, and so I had fluorescent light. And so the blue wasn't really blue. It was more black. And then when I made it work, well, you see, my son's pants disappear, the hair disappears. You can look right through my daughter's eyeballs. And here we're simply taking each of the individual pictures and applying the chroma key effect, and then adding the frame to our frame sequencer to play out the movies. And here's the resultant movie. So see, my son's pants are gone, her hair is gone, and look right through her eyeballs into the moon. But it's still kind of a fun effect. Okay. So as I mentioned, now what we're doing is using media computation with other approaches as well. Alice, as an example, is an environment in which students learn to program by doing storytelling in a 3D environment. This was developed by Randy Pausch at Carnegie Mellon University. It's been changed into more of an introduction to programming approach by Wanda Dan and Steve Cooper. We got this idea. This is actually, I should point out, the original talk at GDCSE was given by myself and my wife, Barbara Erickson, and this is her part. She's the one working with Wanda and Steve to integrate Alice with media computation. And she was the one who came up with the idea of, well, how do you help students go from Alice into more traditional textual programming in something like Java? How do you help students make that transition? Well, one way that there are classes that are doing that, and you take 7 weeks of Alice and then close the Alice, we're starting with Java. And you hope that there's transfer between concepts of variables and iteration and conditionals and things like that. The approach that Barbara has been developing with Wanda and Steve is to say, let's think about Java or media computation more generally as the special effects studio for Alice. You want a particular sound? Well, we can generate all kinds of sounds in media computation. Why don't you generate the sound there and then bring it into your Alice world? Do you need a particular visual effect? You can develop it out there and bring it in. Or maybe what you do is you generate an Alice movie, and all those lighting problems with Chroma Key, you can get perfect lighting in Alice. You can set up the lights any way you want. You can have the background any color you want, and then you can do Chroma Key with that. So here's an example of merging live action with an Alice character. This is the Alice character, in case you hadn't followed, and we simply create a Chroma Key background. Oops. And here's my daughter doing the funky chicken with the chicken. Or the reverse of that, this is an Alice world where the little characters are complaining about the T-Rex frightening them. And what we're going to see is that they took a picture of this one young man lying on his chest in front of a green screen, and he simply gets chroma keyed into the scene. And so you can see that the idea of media computation here is to enhance what's going on with the Alice world, and then it makes it for an interesting moving back and forth, using storytelling continuously as the context, but using the programming with media computation as being the textual side, the technical side, and then bringing the images back in. One of the things that we found, I'm going to show you the results from the media computation in a little bit. One of the things that we found after we started developing these contextualized approaches for the engineers and for the liberal arts majors is that they were sometimes passing CS1, succeeding at CS1, more than our own computer science majors were. That they were succeeding at CS1 more than our own were. So we were looking for a way of contextualizing CS1. That's when we started getting involved with the robotics effort, working with Deepak Kumar and Doug Blank at Bryn Mawr. The idea being is that robots are a context that computer science students recognize as being valid. This really is computer science. We know from our assessments of these students that the students come out saying, I am learning computer science. I'm using robots to do that. And that's the kind of thing that we're after. The folks developing this, Jay Summit, Deepak Kumar, and Doug Blank, are developing the curriculum, are really coming up with great things. Doug Blank held a PeaceBot demonstration at the Franklin Institute in Philadelphia. I don't know if you can read these signs. They say things like, make code, not war. And then at Georgia Tech, we've been putting together these complicated plays with the robots as the characters, wearing various costumes. What Doug in particular has been doing with Miro, the language that they're using, is that he has been creating porting the media computation primitives to their version of robotics. The robot now has a camera on it, which leads for this absolutely fantastic assignment. Grab 5 robots, 5 students and their robots, you can't get the robots without the students, and put together a movie where one of the robots is the camera person. How do you zoom? You point and you go forward. It's really great. And then afterward, they have to do some media computation. It's actually quite complicated. They're really dealing with synchrony and concurrency and how do you make sure everybody's in the right place at the right time. And then afterward, they do media computation with what's going on. It's very creative and it's very collaborative. Here's an example of one of their movies, or part of one of them.
You're traveling through another dimension. A dimension not only of sight and sound, but of mind. A journey into a wondrous land whose boundaries are that of imagination. That's the signpost up ahead. Your next stop, the Twilight Zone.
So we had this wonderful situation that we'd never had previously. Students from liberal arts, architecture management, were passing CS1 and saying, could I take some more, please? And particularly they told us, and this is something I'll get back to when we get to the assessment data, they were telling us they didn't want any more computer science, they wanted more media computation, which is actually kind of a frightening thing, that they really saw these as 2 separate things. So the next normal course that one would offer would be a data structures course. So we decided to offer a media computation data structures course. The driving question for the course is, a little bit down here, how did the wildebeest charge over the ridge in The Lion King? If you're familiar with Disney animation, you know the answer to that question is that this was the first time that Disney did not draw their own characters. Those wildebeests were all were all modeled on a computer and then simulated in a herd situation. That's what we teach, because it takes linked lists and networks and graphs and trees to be able to model a scene. It takes stacks and queues in order to be able to do the simulation. We spend 15 weeks constructing the wildebeest charging over the ridge. Or sometimes we'll do things like, in this example, this is actually an example taken from The Hunchback of Notre Dame, which was also done with a similar technique, where perhaps the bad guy walks into the room and the villagers just step out of the way. And we're doing this probabilistically. Their agents are just milling about. And when they see the bad guy come into the room, they leave the area. Well, not all of them. The knights are programmed to go attack the bad guy. So these are screen caps from the making of. And what you can see is that to model the wildebeest, we need networks and trees to model the scene. And then we create herd simulations. And actually on the making of DVD, they actually show you that the way they work out the algorithms is with what they call bugs, which are very similar to the turtles that we use. And so in the class, we do disease propagation simulation, predator-prey simulations, even political influence simulation. Who wins, the red states or the blue states in the next election? We do a lot of the same kind of open-ended assignments, but now we're requiring students to use objects and agents. This is a class that we've been teaching in Java. So here are similar collages to what we saw previously. When you saw the previous ones, you may have been thinking to yourself, I could do that in Photoshop. These are a little bit more cool, more sophisticated. So these, for example, are not flowers. Rather, it's this baby picture spun on its axis and dropped regularly. In this one, the student took a picture of the Eiffel Tower and then negated it, and then did I think this one's edge detection and then negation of that. And then she took turtles and walked across the surface and dropped little tiny copies of the Eiffel Tower. Now, yes, you could do this in Photoshop if you really want to sit there and carefully scale and drop 100 images. This is really algorithmic art. This is images that one can only create using a procedure, which is a really compelling way of doing it, I think. or of motivating procedures. Okay, so let me talk a little bit about some of the data. In general, media computation students are more motivated and engaged based on retention data and interviews, and find the course social, creative, and relevant. I'm putting that in quotes because we're going to come back to that. This has been a result that is thankfully been replicated at several different institutions now. In fact, people at the University of Illinois at Chicago just presented a paper on this at SIGC last Friday. That in their own class, they're using a media computation approach. And that one's particularly exciting because those students, it's a majority-minority classroom. It's majority African-American and Hispanic students. Excuse me, and they're finding similar success that moving to a media computation approach has improved their retention, has made the students more successful and more interested in computer science. We also know that students in both of these kinds of contextualized courses program outside of class. Surprisingly, perhaps not for some of you who think about it, the engineers jump from start programming with what we give them in class immediately. They do it the same semester. They're programming outside of their CS1, which is actually quite striking until you realize they're taking calculus, often multivariate calculus. And they've never been able to see what they've been doing before. But MATLAB has wonderful visualization capabilities. And so they start graphing and doing 3D images right away. With the media computation approach, we did a follow-on a year later after we started with the course and found that students told us that, yes, they were about 20% of the respondents were programming afterward without having any other CS classes, which is a really cool result. Students in the media computation classes, they spend extra time on the homework, they tell us, quote, because it's cool, because they get interested in the assignment. I taught this class one summer on a study abroad at Oxford. I had a small number of students and I had lots of office hours. And the students would just take in their laptop and sit down next to me at office hours. And I said, do you have a question? They said, no, but I thought I'd start the assignment and then you'd be here if I had any. And it was great. And so I got to watch how the students develop things. And they'd show me, so what do you think of this? That's great, you're done. No, it's not what I want yet. And so the students would spend enormous amounts of time on their collages, on their music, on their movies, to make it look just the way they wanted. And that's, I think, one of the real benefits of this approach, that the students are motivated to get it the way they want it to get, and that leads to more time on task, and we hope more learning. Andy?
Cases where, like, Yasmin confided a study where she allowed students to build games in Logo. And I remember one of the, Michelle, I forget her last name, did a similar study, did an add-on to the study where she had the students keep journals of their expectations for the day, and then afterwards what they actually achieved that day.
Yeah, IPREGÇÖs did something similar in the very first version of that. Yep.
So do you find that your students ever have unrealistic expectations of what they think, what they can do versus what they think they can do?
Absolutely, and so they end up turning it in at the last minute without everything implemented that they want. But they've actually had it working from early on, and that's a really positive thing. So typically the way that, I mean, I can speak to a little bit about how the students actually program in this class. I could show you an example of that summer where I asked them when they made movies to make something which corresponded to an event they had while they were in Europe on the study abroad. And the students scanned in a postcard of Rome and then took a picture of herself and a beer mug because she went on a pub crawl in Rome. And so this beer mug chases her all across the postcard. It's really very cute. But in the middle of this, a red and blue rectangle appear on the screen. Why did the red and blue rectangle appear on the screen? My students who knew media computation in the back of the room know exactly what this is. The first thing she did is type in the example program, which moves a red and blue rectangle, and then started modifying that to make her picture. And she didn't dare remove the red and blue rectangle, because who knows what might have happened had she done that. Which, you know, Ed Lazowska gave the final keynote at SIGC, and he mentioned, you know, 80% of all coding is modifying somebody else's code. It's not a bad thing for them to learn programming by typing in existing code and then modify it to get to what they want. Given a little bit more time, she probably would have gotten rid of the red and the blue. But it wasn't worth it to make sure she hit the deadline. So I think the deadlines force the issue. They make them finish. Sometimes it leads them to have to learn something new. The faculty who are teaching this class now, I haven't taught this class in a while, so when I show you the numbers, these are actually not just me teaching it. So it's not just a Gauss-Dial effect or, you know, the developer teaching the class. The teachers teaching it now, Monica Sweat and Colin Potts, invented a really cool new kind of collage assignment. Build me a flag, preferably of a country that you care about, your heritage or where you're from. So like a Mexican flag or Italian flag, but take 3 images, make them, size them so that they're the right size rectangles, and colorize them so that it looks like the flag. It was really very compelling. And we shared this on the MediaComp teachers mailing list. And someone at the University of Northern Iowa who had a class that was 50% not English-speaking student, not native English-speaking students, so from somewhere else, gave this to them and said, use your own flag. And the students, he said, they really got into it. They found it very motivating, except the students from Saudi Arabia had a very hard time getting the Arabic figure in the middle, I don't know what it is, to show up. So they had to actually go teach themselves Chroma Key so that they would be able to put the symbol correctly in the middle of their flag, which was not a bad result to have happen at all. So it gets back to spending extra time. I mentioned here briefly the architecture course. Another course where we're exploring the contextualized computing education ideas is that we're now teaching a computer architecture course for students where the students program a Game Boy. In any computer science course, you have some course where you learn how to program at the bare metal, no operating system. How does the processor work? How do you load registers? How does memory map? Typically, you do this on a pretend processor. There's a number of pretend processors out there, and there's simulators for those. We decided to teach this course, particularly for our new computational media majors, programming a Game Boy. A Game Boy has no operating system. You have to program pretty darn low to make anything work on the Game Boy. And the students go bonkers with it, and they spend a lot of extra time on their assignments making them look cool, which is a really cool, interesting result. So if you remember those earlier numbers that I showed you, we're doing a lot better than the 60 to 70% that we had previously. And overall, we're better than 85% in terms of our success rate. And you'll notice that there is virtually no difference between the men and women in terms of fail rate in this class anymore. Now, to compare these to the 60 to 70% that we saw for the original class, so the original was in the 60 to 75% range, is a little bit of comparing apples and oranges, because that was everybody on campus, and this is just the liberal arts, architecture, and management majors. So if we look at just those majors, we see a much more dramatic story. So in the original CS1, management majors were succeeding at a rate of 48.5%. Yes, that means that less than half would get through each time, and that includes 2-peats and 3-peats. Under the media computation, the majority of the students are succeeding each time, a great majority, 87.8%. Don't be too, people when they look at this say, what the heck, don't history majors like computing at all? This is very small numbers. We don't have a whole lot of history majors at Georgia Tech. And I should also point out that this is actually, this set of numbers is over a 3-year period, and this is over a 2-year period. So this is not a single teacher. This is a lot of different teachers using similar approaches. This is from the follow-up survey a year later, where we asked students, did the class change how you interact with computers? And we realized that the problem was actually a bad question. Well, no, I use a keyboard and a mouse. It hasn't changed much how I interact with computers at all. But we did get some great responses nonetheless, that the majority of the students said yes, and they told us things like this. It definitely makes me think of what's going on behind the scenes of such programs like Photoshop and Illustrator. And that's the sort of result that we think that you want when you teach a computing course to non-majors. You want them thinking about how the computing is playing a role in the things that they're doing on a daily basis with the applications that they use. Okay, some of the other results. We don't know if they learn the same. We really don't know. It's a very difficult thing to measure CS1 learning. And I talk about the lack of a common reality. Let me give you an example in terms of physics. So imagine that we've got 3 different ways that we want to teach physics. And we split it up into groups, and we say, okay, what happened there? Okay, and it doesn't matter what the approach is. I might tell you a story about kinetic energy and potential energy. I might tell you a story about horizontal velocity and vertical velocity. Hopefully none of us is going to say, well, the air pressure pushes down at the bottom, and that's at the top, and that's why it turns over. How do I express to you computation in a language-independent way so that no matter what your approach is, you can try to explain it to me? For a CS1 major who only has seen one language, it's very difficult to express computation in a way that they can talk about what's going on and try to explain it to me in a way that is language independent. I actually have a PhD student, Allison too, who's working on this problem. She's trying to come up with a language independent way of measuring CS1 knowledge. We're not there yet. It's actually very difficult to come up with a reliable and valid way of doing that. She's trying to use a pseudocode approach, teach a very simple pseudocode on the first page of the test, so that they might use the pseudocode for all of the things that come afterward. Obviously, you can't go very deep into CS1 knowledge, but we're after the surface level stuff just so that we can get a baseline comparison between approaches. So we're hoping to get to that. While engaging, the majority of students do not find the media computation courses relevant to their degrees or professions. So I told you earlier that Margolis and Fisher found that most people don't find computer science courses, traditional ones, very relevant. What does it mean to be relevant? We asked the question. We wanted to ask people, right, so do you find this relevant? Oh yeah, this is relevant. Then we started asking people on following semesters, in what way is it relevant? Does it help you get your degree? No. Will it help you with your profession? No. I mean, in general, I mean, it depended on the class, but in general, it was not a clear yes. The clear yes was, is this relevant to your life? Majority of students say yes. And we realized that what we really got to was not that this impacts you're going to succeed better as a liberal arts major. You're going to be a better historian, a better international affairs major. Rather, they say, I live in a digital world. I live in a world with lots of digital media. And I appreciate now understanding what's going on with that digital media. That's the story that we're getting back, which is I think it's a reasonable place to get to. But it's a much more subtle notion about what does relevance mean for these students. As I mentioned earlier, students do distinguish between, I would like to take more media computation classes versus I would like to take more computer science classes. Very first semester, it was something like 60 to 70% of the students say yes, they'd like to take more of those. Only 11% said they'd like to take more computer science. To this day, it's still the case. We do get students who transfer into computer science who do take more computer science. It's only about 10%. But we have much more of them succeeding and taking their computing knowledge into the rest of their lives, which is a positive outcome. Andy?
How do you measure their communication skills? In some sense, like, do you think that they're able to better communicate to others about the kinds of computational concepts they're learning in your class?
Wow, that's a really neat one. I don't know. I've never tried to explore that. That's interesting. So I'm teaching this semester a graduate course on computer science education research. And I actually have one student who's interviewing intro computing courses, especially students in the media computation course, showing them two pictures and say, tell me in English what it takes to get from here to here. Now, he's mostly interested in replicating like John Payne's work and Lance Miller's work to get a sense of how do people express those processes in English language. But maybe he'll get at some of that as well. I don't know. That's a great question. It's not, I mean, if you think about it, it's not typically what we go after in CS1. Right? If we actually ask our CS majors, how well can you express computation after your first course, we'd probably be dismally depressed because their communication skills in general are not all that great after the first semester. But I think it is an interesting comparative question to ask.
To Congress. These are the people who are going to be CEOs of non-computer tech-related companies who hopefully will have some notion of what it means to do computation and a way to spread it to others to indicate that it's important.
You're right. I think that's a great point. Now, we are getting them in their first semester. So, you know, their writing skills might not be out, but it's a great point. I mean, it really is important. And we do get to, I mean, I'm not going into much detail on the curriculum, but we do spend time, we spend about 10 weeks of the semester on the programming class, and then we spend 5 weeks on all the computer science issues that arise from that. So, like, one of the questions is, why is my movie code slow? And it's the case. I mean, processing over 100 of images, you know, 640 by 480 takes a long time, particularly when you're talking about an interpretive language like Python. But we can get into discussions of algorithmic complexity. And I think it's important that we actually hit on those sorts of things, because for most of these students, this will probably be the only computing class they ever take. Okay, so the bottom line. So media computation is an approach to trying to teach computing, mostly for non-majors at Georgia Tech, but other schools are trying it with majors as well, to teach computing through image, audio, and video effects. And from a gaming perspective, we're teaching the stuff that your gaming engine and your API might do, and it's clearly something which we're getting high success rates in terms of retention. Students are buying into this. It might be a way of thinking about pre-gaming, or even, as John's been pointing out to me, pre-film. If you want students to play with film ideas, this is a nice way of getting those ideas about what kind of computing is going into film at an early level. We're finding it ties easily to other approaches like ALICE and robotics, and perhaps gaming as well. The assessment results are promising. The retention result in particular is very strong. That there's about a half dozen schools now that have replicated some form of this study. Australia National University, University of Illinois Chicago, South Carolina State University, Gainesville College, and are similarly finding these increases in motivation and in the students getting through the CS1 class, which is a big win all by itself. Here are URLs. I should mention that For CS faculty, we are offering workshops paid for by the National Science Foundation for free. We pay for a big chunk of travel, about $250, and all the room and board. It doesn't cost anything. And we'll teach you about how to use these approaches. Barbara teaches these with our Institute for Computing Education at Georgia Tech. That's the ICE-GT. The Tea Party site is the one for Allison Media Computation work. It's my group site, and where we have more information on media computation, including MediaCom Teach is linked to all the various reports from the other schools on the use of media computation. Thank you very much. I'd be glad to take any questions. Yes, sir.
So I'm looking at this from a, obviously, a computer science point of view. I'm thinking CS1. Obviously, you must provide a lot of libraries to just load the image off the disk and all that other stuff too, because it's one thing to, go through the array and change all those things, but reading the bitmap header and finding out where the data starts and the file system and all that other stuff that goes on has got to be provided by some kind of library.
Absolutely. We're doing all of that for the students because now you don't have to. There are places who are using a similar approach where, for example, if you assume a BMP file, the header is pretty simple. Reading in all of the pixels is pretty simple. There are places that teach that. Jennifer Berg at Wake Forest University has actually been teaching classes. You might think about it as Media Computation ++ at the junior or senior year level, where they talk about having the students figure out JPEG encoding and decoding. That's clearly computer science stuff. We want students to be able to make a picture and start manipulating the pixels on day one. That's right away. So yes, we do provide a rich library. We can read JPEGs, we can write JPEGs, we can read WAV files, we can write WAV files. We can read some other formats. We can read GIFs, we can read some kinds of MP3s, and the students can manipulate them and write them back out. So yeah, it's a lot of scaffolding that we're providing up front. And I think that's a necessity if we want this to work with non-majors. Yes, Andy, please.
Have you ever thought about sending your students from your media to computation class to like a lecture or talk in computer science that's given for advanced computer science students to just see, given the concepts they're learning in this class, do they think they'd even get anything? Like how much could they get out of one of these lectures to even know what they're talking about at all?
It's a great question. I mean, we'd have to be a contextualized lecture. But every once in a while, we're fortunate enough that Wayne Wooten, one of our alums, comes back and visits and talks about whatever the most recent Pixar movie is and explains what they did to Render Man in order to make it work. And Wayne is really quite a good teacher in himself and does a great job of explaining this in ways that even those of us who didn't take a whole lot of computer graphics can understand. And I've had my students go to attend that lecture and really come out very excited about the kinds of things that he's talking about. I actually use some of his examples myself in my class. So we talk about them blowing up the terabyte buffer in Linux when they were doing The Incredibles, because they were object modeling all of the things in the waterfall scene where the monorail goes in behind the waterfall, and that each of the drops is an object with 1 e to the -6 transparency, and it's only white when you got about 1 million of them. And the students get the sense of just how much memory that is and why that blows things up. So yeah, I think that if you stay within the context, they're actually pretty good at handling some more sophisticated computing ideas. John?
Which of the two languages would you say has a stronger pedagogical strength, and which of the two languages has the strongest strength for manipulating the media?
Python is clearly a lot easier to get started with. So the very first time Barbara taught the Media Computation Java class, this was to high school teachers who want to become computer science teachers. We got involved in this because the State Department of Education in Georgia wanted to have more computer science teachers. Computer science teachers in general are management or liberal arts majors. Gee, does anybody have a way of teaching them computer science? So they came to us, but they said they wanted to be in Java because they wanted teachers to work in the language of the AP. So that's why Barbara did this book. So the very first week that she's teaching this, I'm taking the kids off to summer camp. Okay, so she's teaching it, and I'm calling her each night, and it's not going well. They're really struggling with public static void main and declaration of the type. And then on Thursday, so you saw earlier, the computer science teachers with Python start in the morning, and at lunch they're doing image manipulation. On Thursday, I call her up, and she says, it happened. They finally got it. They were working on their collage. It takes more time, so it took them 4 days to get to being able to do collages. But she said that she showed them horizontal and vertical mirroring, And then some of them asked, how do I do diagonal mirroring? She said, go ahead. And she says that a whole group of them wouldn't leave at lunchtime because they were trying to figure out how to do diagonal mirroring. It's like, yes, it's the same effect that we get with the undergrads. We're seeing it with the high school teachers as well. So Java has a lot higher cost to being able to do things like this. On the other hand, the Java code is faster. One of the things that's really interesting is when the media computation intro students take the media computation data structures class, we ask them at the end, which did you prefer, Java or Python? And they almost always say Java. And being a Python fan in my heart of hearts, I was really disappointed by that until we started doing interviews with them and realized that it's because we didn't get that far in the Python in the first semester. What they really liked was calling methods on objects and being able to say object.method do this, or object.method.method, cascading that. They really loved that, and they thought that was something that Java could do and Python couldn't, because we didn't get into all of the object and method manipulation that deeply in Python. So like, oh well. But yeah, the Python really works very well for getting people started. Now that said, Myro, and there have been other people, the University of Toronto, are porting all of the primitives that we use in this book to CPython. And that can be really fast, depending on the libraries that they're using underneath. So I don't think it's the case that Java is always faster than Python. A lot has to do with the underlying implementation of the very libraries that you're talking about. Yes, sir?
You get any of your non-CS majors to actually switch to CS after that course?
Yes, I'm glad to, because Blake in the back row here was an architecture major, right? Originally architecture, who took 1315, perhaps against his will, I don't know. It's required of all the architecture majors. Fell in love with it, became our TA for many, many semesters. I can show you all kinds of movies that have been generated based on assignments that Blake created, and he graduated last May, right? Year ago May. That's right, with his computer science degree from Georgia Tech. And now he's here, so he's doing pretty darn well. So yes, it certainly does happen. I don't have exact numbers, because it's actually fairly hard to track these things. For one thing, there's FERPA issues in here, the federal privacy law, that if students admit to me that they transferred, that's great. I can try to track them down, but depending on what major they go into and how many years separated it is and whether or not I got permission originally to track them, it's fairly hard to tell. I do know that students do transfer. I don't have a sense of how many. I certainly know that it's not a lot, just from the fact that only about 10% of the students go from the first class into the second class. I can't imagine that this, we're certainly less than 10% are becoming computer science or computational media majors. Andy?
What happens to the ones who don't succeed at this class? Like, why are they not succeeding?
That's a great question. So last semester, we had the worst fail rate we ever had in the intro media computation class. I sat down with the teacher to go through all of the data to try to understand why. We had a large number of students last semester who, after homework 2, stopped doing anything and didn't drop the class. They didn't come to any more exams, and they didn't take any more homework. They just gave up, yes. I'll admit this, even though it's anecdotal and not particularly happy thought. When we designed the computational media degree, we originally designed it thinking that we'd have people who could succeed at computer science but really wanted to have a more expressive kind of degree. They wanted to talk more about creativity and expression. What we're finding that we're getting instead is, to some extent we can't really tell, we haven't really measured this, is liberal arts majors who think that they can get through a computer science class and decide that computational media is a better degree to come out with than literature, culture, and communications or literature or some other major. And so what we find is that these are students who really don't like programming and really are griping about having to take any program, which seems strange. You took a degree in computational media. So there is the teachers are telling me that I'm getting that a lot of it is whining from these majors who find themselves perhaps in the wrong degree. I don't really know at this time, but in general, it's fairly small percentage. I mean, certainly less than a typical CS1. Stuart.
A slide or two back, there was a tantalizing word or phrase which may have related to the game crew's context. Get that one. There. ... gaming. Following your attendance at a gaming cruise, what's your current thinking about how applying computer gaming as a context for learning computer science, which there's a lot of work going on? How does that, could you compare and contrast that with media computation?
Well, I don't know enough about the data on gaming as a context for CS1. I mean, Jamie knows this a lot better than I do. What I was actually thinking about, and John certainly, what I actually meant by the ... is thinking about media computation plus gaming, or media computation as a lead into gaming. I think media computation is a class that works pretty well as a context, and we find that it integrates well into other contexts. I was actually contacted, folks at the University of Illinois Urbana-Champaign were teaching a media computation class this last semester, and they said, you know, if you simply made the window where the picture is, if you could let me have access to mouse clicks, I could make a game. And I think that's a viable thing, and we're going to explore making those sorts of changes to the underlying API so that we're thinking about some sort of a polling mechanism where you can get the mouse status, and that would be enough to do that if you wanted. But since this does lead into the kinds of things you do in gaming or in film contexts, it seems as if it could work as a pre-gaming kind of activity. So while I don't know much about gaming as a CS1, though Diana Zhu from Bryn Mawr had a really nice talk at GDCSE where she talked about they explore storytelling with Alice, gaming, I think they use Game Maker, the robotics, and there was one other context, the media computation. And she talked about the differences between them. It was a very nice talk. It's in the proceedings. Andy.
Class between media computation and like playwriting or media computation and movie making? Like,
Well, in some sense, that's exactly what the Alice in media computation is getting to, because it's really about storytelling with Alice and then bringing the media computation in order to be able to get the special effects that you can't get from just plain Alice. Steve Cooper taught a version of the class last year. Barbara's at a little bit of a disadvantage. So Barbara is our director of CS Outreach, so she mostly works with K through 12 with other teachers. She's not in a position to try it out herself in a classroom. And now, as you know, Steve's now at NSF, Wanda is now at CMU leading up the Alice project. So we're kind of looking for classes to try it so that we can try this approach. From the class that Steve tried last year, it was pretty successful. He said he had one of the highest success rates he ever had from his CS1 and the most students who went on to the second class. Which actually, I should mention, anecdotally, one of the things that we're finding, and we're only getting this result now, and we would never see this at Georgia Tech because we mostly teach media computation in non-majors. The places that are using these contextualized approaches with CS1 are seeing a huge uptick in the students going into their CS2. Bryn Mawr has been using the robotics approach for the last 2 semesters. This semester and the coming up semester, they have the highest CS2 enrollments they've ever had, like by a factor. They showed Doug showed the graphs, and it's like doubled than the highest they've ever had before. It's just absolutely amazing. Gainesville College, which is the very first school outside of Georgia Tech to adopt media computation. It's a small 2-year school. They almost never offer a CS2 because they might only have 2, 3. He had 12 students last semester who wanted to go on to the second class. So it's really quite intriguing that there might be something about an effect of getting students to want to continue on. And because we're dealing with non-majors, I mean, if you sign up for some place like Georgia Tech and say, I want to be an architecture major, you're unlikely to say, tomorrow I think I want to be a mechanical engineer or a computer scientist. They've made choices already, and so it's harder to get them to change them. If you go to some place where the students haven't made a declaration of a major yet, we're seeing, or have in computer science, I think we're seeing an effect of contextualization help pulling them along. You had a question, Kent?
A question about this combination of Alice plus media computation. How young can you go? Does this work in middle school, for example, or is it high school?
So currently they're doing all the development with Java because they see this as a context for advanced placement in classes. But there's no reason why any of it couldn't be done with Python. So in that case, could it be done middle school? I don't see why not. I don't know that anybody has tried. I think that it's viable. You'd probably want to think about a follow-on course to traditional Alice. With an undergrads, you can do it, both of them in 1 semester. That's what Steve Cooper found when he tried it at St. Joe's. With middle school students, maybe 1 whole semester of Alice and then 1 semester where you merge it so they know the Alice well. I don't know. I think it's a fascinating question and well worth exploring. We're not currently there. Stuart.
As you're driving this computational thinking agenda, just for the sake of pattern matching and simplicity, media computation sounds a lot like computational thinking. Do you have any comments on whether you're a subset of computational thinking, just one way? This is the one true way to do computational thinking. Do you have any
So I think that computational thinking is sort of like what we used to call algorithmic thinking, but But I kind of like the computational word better because particularly what I find when I work with the non-majors, for a lot of the non-major, non-computer science applications, the algorithm itself isn't the big deal, right? So like for people manipulating pictures, the notion of breaking a picture up into pixels with each having a red, green, and blue value for their color, that's a big deal for them. That's something that just blows their mind. And that's about data representation, less than so about algorithmic. So I think that I would say that there's a lot of computational thinking going on here. I think the results we're getting clearly suggest that that's what we are imparting to these students. They are not coming away saying, I want to be computer scientists, I want to be software developers. They're coming away saying, this helps me lead my life in a different way. And that's what I think is at the heart of the computational thinking. John?
USC's film school, this would clearly be computational thinking for those folks as they apply computer technologies to manipulating film.
I hope so. It'll be fun to explore.
Andy?
Earlier, how old do you think you can go?
How old could the kids get?
Could you teach like your grandparents or something like?
I just met at SIGC a guy who Daniel. I'm not going to remember his last name, and it's a college starts with an A. I met a lot of people at SIGC, but him in particular, he is using this with adult education classes to try to draw students back into getting their undergraduate. So it's real. I mean, you think about it, it makes sense. If it works with high school teachers to draw them into computer science, why wouldn't it work with adults who are thinking about possibly going back for a computer science degree? So I think that's an absolutely compelling result. Maybe one other quick example from SIGC that I was really struck by. One of the things that's nice about coming with an approach like this is that the teachers can be really creative with it too. So I met a graduate student from, somewhere near the University of British Columbia, but not there, a smaller school, where her dissertation, she's working on a PhD where she is separating audio streams. And so she's teaching a CS1 using our media computation stuff where the context is CSI. And the problem that she's given them, she said this week, they're actually working on it while she was at SIGC, or last week. Here are 5 sounds. They come from 5 microphones at these places around the bank. At what time did the bank robber arrive? And what's really cool about that is that it's using the same primitives, but it's about analysis rather than synthesis. And you could imagine going much further than that. I'm sure that some of you may make the same mistakes I do. You go to some place like a church where you can't use a flash, and you take a picture, and the picture turns out just absolutely awful, and then I load it up into Picasa, and I press I feel lucky, and I can suddenly see everything there. What filters just happened there? Can you imagine giving your class pictures that are staged? This is the bank robber working on the safe, right? It's a dark picture. Find the image. Find what's going on here. You could really teach this whole course from an analysis perspective instead of a synthesis perspective, and it would be really fun. So cool things that I learned at SIGC. So yes, I believe that it really can be used with adults, and the one guy is really trying it out, and it sounds great. Questions? All right. Thank you all very much.